Hey, let's start today's session. Uh, Today we will continue our inferential statistics. And today we will talk about confidence interval. What is the confidence interval and what are the conditions and how do we find it and how do we interpret 95% confidence interval or confidence interval? Okay, so first, what is a confidence interval? The formal definition is it is a plausible range of values for a population parameter. Okay, so when we talk about inferential statistics, what's available is our sample. So, but we don't want to know about sample, we want to know about population. So we need to estimate from our the population based on our sample. So we need to generate a plausible range for the population parameter. So this range, okay, this range of value is called a confidence interval. Okay, so why a range of values? Okay, let's take a moment and look at these two pictures. Okay, so here we want to, so we are using a stick, okay, and then trying to hit a fish in a river or in a stream. Okay, so we use a stick and point it to the fish. So imagine this: if you're going to poke the fish with a stick, then it's likely that you will miss. Okay, that is what we call a point estimate. Okay, so we only estimate one point, and there is sampling variability. Due to this sampling variability, we were most likely to miss the true value, okay, the true value of the population parameter. On the other hand, let's see this man, okay, he catched fish with a net. So if we make it larger and trying to capture the true value of the population, like this man did, it is more likely that we will capture the true population parameter. So that's the idea here, okay? If we report the point estimate, okay, what is the point estimate? You can say it's a mean or you can say it's a proportion, okay? But if we only report a point estimate, we were likely to miss the exact population parameter or the true parameter, okay? So anyway, in reality, we don't know the true parameter. So we need to give it a range so that we capture the true population parameter. Okay, so if we report a range of plausible values, we will have a good shot at capturing that parameter. But again, let's take a look at this. Okay, this is X bar. X bar is mean. Okay, mean of a sample. Okay, and again, we want to give it a range. Okay, like this bar. So in order to capture the true value. Okay, so where did this bar come from? This bar came from the central limit theorem. Okay, this theorem is based on the sampling distribution we discussed yesterday. So based on the sampling distribution and central limit theorem, our sample mean our sample has a distribution, normal distribution, or with a mean approximately to the population mean, and with our standard error is the same as standard deviation divided by square root of sample size. So this is based on our sampling distribution we discussed yesterday. Okay, so according to this 68, 95, and 99.7% rule, we now know that what is our point estimate? Our point estimate is the mean of the sample, okay? Because based on this central limit theorem, our sample mean can be approximately equal to the population mean. So, okay, whatever mean we have from the sample, we can say it is the point estimate for a population parameter. And then we're trying to give it a range, okay? We're trying to give it a range. What is a range? We want to capture the 95% of the time. Okay, we want to capture the true population value 95% of the time. That's why we put it to standard deviation. Okay, for the 95% CI. Okay, for the other percent CI, this value will change. Okay, this constant value will change. So anyhow, we are discussing about 95% CI. So this value will be point estimate plus or minus 2 standard deviation, okay, or standard error in this case. Okay, so what we already seen this yesterday. What do we call this this value behind the plus or minus? It is called a marginal error. Okay, so how likely we want it to miss the true population value. That's why the marginal error. Okay, so we want to capture the true population parameter 95% of the time. So the remaining 5% of the time, 5% we can miss. Okay, we can. It's likely to give an error. That's why we call it 95%. So we are only 95% confident that this will capture the true population parameter. Okay, so the other 5% we're not so sure. So that is what it basically means. Okay, so here's example. So one of the earliest example of behavior asymmetry is a preference in human for turning the head to the right rather than to the left during the final weeks of gestation and for the first 6 months after birth. Okay, so basically it said that we tend to turn our head to the right rather than to the left. So this is thought to influence subsequent development of perceptual and motor preferences. And then they did a study and they recruited 124 couples, and the study found out that 64.5% of this couple, turn their heads to the right when they kiss each other. Okay, so the standard error associated with is roughly 4%. Okay, so we now have a point estimate, which is a proportion. Okay, this point estimate can be mean, median, any descriptive statistics, and then we have standard error 4%. Now, which of the below is false? Okay, let's try to look at this one by one. A, higher sample size with a low standard error. Okay, we already discussed yesterday, right? When we increase the sample size, the standard error tends to narrow. Okay, it's okay. This one is correct. This one is correct. Now the second one, B, the marginal error for 95% CI for a percentage of cases who turn their head to the right is roughly 8%. Okay, so think about this. On previous slide, we already said the marginal error is for 95% CI is 2 multiplying with standard error, right? So standard error is 4. Now multiplying with 2, so we have roughly around 8%. So this is also correct. Now C, the 95% CI for the percentage of cases who turn their head to the right is roughly this one. Okay, so based on our point estimate and based on our marginal error, okay, so marginal error, we should have 64.5% plus or minus 8%, right? Not 4%. So this is false. Okay, so which order below is false? So this one is false. And I'll take a look at this. Number D, the 99.7% of CI for a percentage of cases who tend their head to the right is roughly 64.5% plus or minus 12%. Okay, so I think if you think about this, what is the standard deviation for 99.7%? We got 3 standard deviation, okay, below above the mean. So we multiply 4 with 3, okay, and then we got 12. So this one is correct. Okay, so number C is incorrect. Okay, next. Okay, so what is the confidence interval for a population mean? Okay, what is the confidence interval for a mean? So we basically it's a point estimate, okay, sample mean. And then you plus or minus the marginal error. You plus or minus the marginal error. So this one is the point estimate. This one is the marginal error. So what is the marginal error? It is a critical value, which is a critical value corresponding to the Miller XX%, which is commonly 95%. Okay, you can use other percentage. Okay, 99%, 90%, 85%. But remember, when you reduce the confidence interval, the level of confidence interval, the alpha will increase, and we will talk about this later. Okay. Anyway, what is this marginal error? It is a critical value. Okay, it's very important to construct our confidence interval. That's why it's called a critical value, which corresponds to the middle 86%. Okay, normally 95% of the normal distribution, and then we multiply it, okay, with the standard error of the sampling distribution. Okay. Okay, so that is basically the confidence interval. How do you construct the confidence interval? So what is the critical value? It's basically a z-score. Okay, it's a z-score. So what is the conditions for this to construct this? To use the confidence interval. So basically, this condition is the same as the sampling distribution or central limit theorem that we discussed yesterday. So first, you need to have the independence condition met. Okay, so that happens when an observation is independent of each other. Okay, so you can see whether it is independent or not by 2 statement. Okay, first one is random sample. So if they do a random sampling or random assignment, then observations are likely to be independent of each other. Or second statement is if the sampling without replacement, then the sample size must be less than 10% of the population. Okay, this is independent assumption. And the sample size or skewness, okay, normally as a rule of thumb, we our sample size should be greater than 30, or should be larger if the population distribution is very skewed. But normally we don't really know what the population distribution is really look like. So we need to collect or recruit sufficient sample size greater than this 30. Okay, so we got 2 conditions in order to use confidence interval. Okay, you can construct for any means, but in order to interpret and have no bias, you need to meet these 2 conditions. Otherwise, it will be biased. Okay, the confidence interval will be biased. Okay, let's take a moment here. So what is the critical value or z-score for 95% confidence interval? And we have already done this. Okay. Okay, let's take a moment and draw our distribution. So we have this distribution. This distribution is the standard normal distribution. Okay. And what is the standard normal distribution? It is mean is 0 and standard deviation is 1. Okay, so what is 95% CI? We need to capture the middle 95% CI. Okay, so the true value where we inside this range. Anyway, so what is the middle 95% CI and what is the corresponding Z value? Okay, so at least you can look at the picture and you can see that the value is almost 2. Okay, 2 standard deviation because we want 95% CI. Okay. Anyway, let's take a moment and look at here. So what is the remaining percentages on the other side, on each sides? Okay, so this one has 2.5% and this one has 2.5%. Okay, so we need to find this value on this line. Okay, so how do we find this? We use the Z distribution and look at the percentage in order to find the Z value. Okay, and here, do you remember when we talk about probability, we say that this probability, this is the probability of area under the curve. Okay, but here 95% CI is over the curve. Not over the curve. It is the middle portion between 2 points. Okay, we don't want that, or we cannot find that directly. So first we need to find this. We need to find this portion. Okay, so we got this number which corresponds to the area. So this is the probability for this portion, and then we need to find this exact value. Okay, this value here, and then this value here, the same. Okay, so we have 2.5%. So we look at the Z distribution. So 2.5 is around here. So look at here, minus 1.9, and then we got decimal point. So minus 1.96. Okay, so basically it is the same on the same mark on either side of the mean. So you just give minus and plus. Okay, so anyway, our critical value is minus 1.96. Okay, earlier we learned that in order to be a normal distribution, 95% of the data should be within 2 standard deviation. Okay, so that is why we make that kind of statement. But in fact, when we calculate and put decimal point, it is not exactly 2. It is around, it is exactly 1.96. Okay, it's not 2. Okay, anyway, you can find this using R with Q norm. So do you remember on day 2 we discussed about probability, and then there are 2 functions in R to find the probability and the quantile. Okay, P norm is the probability and Q norm is the quantile. So we have probability value and we want to look at the point or the quantile. Then we use the quantile of normal distribution, Q norm. Okay, and then you plug in the probability value, and then we got the quantile value. Okay, anyway, let's move on to accuracy versus precision. Okay, so we already have a point estimate, which is coming from descriptive statistics. Now we know that how to construct confidence interval, 95% confidence interval for a mean. Okay, so we need to discuss a little bit of accuracy versus precision. Okay, how confidence interval contribute and how the width of the interval means, and what factors influence this width. Okay, what makes it wider or what makes it narrow, and what are the traits of. Okay, let's start with confidence interval. So we take many samples and then build a confidence interval with each sample using the equation here. So point estimate, whether it is the mean or proportion, and then we give it a marginal error, okay, with a 95% CI, okay, it is 1.96, and then we give it a standard error from the sampling distribution. And then we got the 95% 95% of these interval would contain the true population mean. Okay, so you can really do the simulation. Okay, so anyway, when you do 25 times, 24% of the 20, when you do 25 trial, then 24 trial will contain the true value. Okay, this dotted black line is a true value, and then only one will be out of that does not capture the true population value. Okay, that is what 95% mean. Okay, so you did 100 trial, and then 95% of the time, or 95 trials, you are captured the true population, and only 5%. Only 5%. There is a chance that you will miss the true population. Okay. And then we commonly use a confidence interval 1995, 98, 99. Okay, but normally we use 95, and sometimes we use 99%. But rarely, if you use 99%, you need a large sample size. Okay, when you decrease the confidence interval, you will have a flexibly smaller sample size. Okay, so if we want to be very certain that we capture the population parameter, should we use a wider interval or narrower interval? Okay, so the point of having a confidence interval is we want to capture the true population. Okay, say, okay, so why don't you open it? Okay, open it as wide as you can, so that you can capture the true population parameter whenever you catch it. Okay, is it a good idea to have a wider confidence interval? Okay, let's see. Okay, when you open, basically when the 95%, 95% and 99%, let's compare it. Okay, so for 95% you need a z-score minus 1.96, and for 99% the z-score, the critical value is 2.58. Anyway, when you increase the confidence limit, okay, basically it's the confidence limit from -2 to 2 and -3 to some point. Okay. Anyway, when you increase this confidence limit, your width also increase. Okay, the range also wider. Okay, so let's see this example. Okay, so you listen to the weather announcement and say that, okay, today the weather could be as low as -20 degrees Fahrenheit and as high as 110 Fahrenheit. So basically, he's saying that, okay, today can be either very cold to -29 degrees Celsius, or to very hot to 43 degrees Celsius, which is true, which is the true statement, because almost in any day this will be true. Okay, because okay, we are living in a tropical area, subtropical area, whatever you call it, and the temperature will range between this value. So anyhow you will capture the true population parameter. Okay, so is it wise? No, it is not wise at all. It's not good to use it at all. Okay, it is useless. So you cannot know, you don't know how to, you don't know even if you need to bring your code or not. So when you increase the confidence limit, your width increase, okay, the confidence range increase, and it will be more accurate, because most likely one temperature will be there. Okay, so it will be most likely to represent the true situation, but it will be less precise. Okay, it's not precise at all. You can barely use this temperature. Okay, so how do we get the best of both worlds? Okay, we need to increase the precision, also increase the accuracy. We want to capture the true population. Also, we also want to make it precise, okay, so that we can use it. And the only way to do is to increase the sample size, okay? Okay, that's why when you consider a study, sample size is very important, okay? Sample size is really important. So sometimes when we are just looking at the medical records, we just say that this is a routine medical record, we don't need to calculate the sample size, but that is not true, okay? Okay, there are two ways to do the sample size. So why do we need a sample size? We need to know that our confidence level are highly precise and highly accurate, okay? So you can look at the result and say that, okay, whether it is confidence level is too wide or not. If your confidence level is too wide, then your sample size is low. And then you will have a precision problem, okay? Okay, so let's take a look at this example. The General Social Survey, which is a sociological survey used to collect data on demographic characteristics and attitude of residents of the United States. And in 2010, the survey collected responses from 1,154 US residents. Okay, so the sample size is relatively large. And then based on the survey results, 95% confidence interval for the average number of hours Americans have to relax or pursue activities that they enjoy after an average work day was found to be 3.53 to 3.83. Okay, so let's take a moment here and try to determine if each of the following statement is true. Okay, so we have A, B, C, D, and A, 95% of Americans spend 3.53 to 3.83 hours relaxing after a work day. B, 95% of random sample of 1,154 Americans were yield confidence interval that contain the true average number of working hours. True average of hours Americans spend relaxing after a work day. C, 95% of the time, the true average number of hours Americans spend relaxing after a work day is between 3.53 and 3.83 hours. D, we are 95% confident that Americans in this sample spend on average 3.53 to 3.83 hours relaxing after a work day. Okay, so based on the statement here and trying to determine which one is correct or which one is false. Okay, let's take a few moments and think about it, okay? And then you can see the result or write it down in a chat box, and we will see in a few minutes. Okay, so I think we go one by one, okay? What do you think of A? Is it true or is it false? So if you can interpret 95% confidence interval, then you know whether it is true or false, okay? So we got our sample size. Okay, let's say here is our sample size. And then we got 95% CI, okay? But the problem didn't state any point estimate, okay? It gives a range 95% for 95% CI, which is 3.53 to 3.83, okay? So the first one state that 95% of Americans spend 3.53 to 3.83 hours relaxing after a work day. Is it true or false?
False.
Okay, anybody would like to try this? Okay, this is false, correct, right? this is false. Why? Because this is not the definition of 95% CI, okay? So we cannot say that 95% of American, okay? We cannot say that. We can only say that we are 95% confident, okay? This 95% does not tell you about the proportion of the sample size, okay? This is not a sample size. It is how confident we are, what is the level of confidence, okay? When we did trial many times, what proportion of the trial will capture the true population? So that is what 95% CI mean. So we just basically false here, incorrect here. Okay, what about number B? 95% of random sample, and of this 1,154 Americans were confidence levels that contain the true average number of hours and American spent relaxing after a work day. Still false. Okay, here you should take a look at here. It is the 95% of random sample. Okay. I think it is true, okay? I think it is true, but I could be wrong. Okay, because when you did, okay, let's do one by one, okay? We are only at B, so so you did a random sample 100 times, okay? 95% of the random sample were contained, will yield the confidence interval. Okay, basically it means that 95% of 95 random sample out of 100 random sample will contain a true population, true average number. So I think this is correct, okay? And next, C, 95% of the time, the true average number is between this and this, okay?
I think C is correct.
I think this is also correct. And okay, somebody say D is true, but red is false. Okay. And number D, we are 95% confident that Americans in this sample spend on average 3.5 to 2.83 hours relaxing after a work day. So this is the definition that I'm talking. So, okay, let's go next. Okay, wait a minute.
I think C is correct.
Okay, I see.
D.
I think this D is false because this is talking about sample, okay? That is why number D is wrong. So we are 95% confident that Americans in this sample. So we are not interested about sample. So we want to be talking about population. So that's why this is wrong. And why C is wrong? 95% of the time, the true average number of hours Americans spend relaxing after a work day is between 3.53 and 3.8 hours, 83 hours.
I think 95% of the time is that we are confident that true average number, that means the population parameter of hours American. So I think C is only the correct answer in my point of view.
So you think C is correct, right?
Yes.
Yeah, I think so. Okay, anyway, I think it is correct. C is correct. I don't know why. Okay, anyway, so this is how you interpret it. Okay, even you are 95% confident, but when you are not talking about population, then it is wrong. Okay, we should be talking about the population. So the true population parameter should lies between this and this. Okay. But sometimes, because this is not our first, native language, it's a little bit confusing. how they phrase the English sentences. Okay, anyway, let's go forward. Okay, next we'll okay. So we were talking about sample size versus the accuracy here. Previously, we talked about the marginal error. Okay, what is the marginal error? The marginal errors is basically the multiplication of the critical value and standard deviation divided by square root of n. Okay, so anyhow, we want the sample size. So when we arrange the sample size, we got this formula. Okay, so anyway, look at this. Look at this association. Okay, first look at this association. So this is the marginal error. Okay, so the marginal error is inversely proportionate to the square root of n. Okay, which is basically n has the relationship of marginal error squared. Okay, so when you increase increase the sample size, your marginal error will narrow down. Okay, so we're narrowed down by 2 times. Okay, not 2 times, it's square root terms, in the square root terms. Anyhow, this way goes like that. Okay, but when you increase your sample size but to the certain limit, okay, you increase your sample size up to 5,000, say 8,000, but beyond 5,000, your standard error will barely change at all. Okay, so that's why it is not a good idea to increase to include all the entire population, because it doesn't make any change to the standard to the marginal error. Okay, so the accuracy, the precision will not change once you pass the some limit of sample size. So you don't need to include everyone in your population. You just need to set a sufficiently large sample size. Okay, so this is how we calculate the sample size for a mean or for any estimate. Okay, for proportion, for mean, we can use this this formula. Okay, anyhow, let's take a look at this example. So there are a group of researchers. There's a group of researchers who want to test the possible effect of epilepsy medication taken by the pregnant women on the cognitive development of their children. As evident, they want to estimate their intelligence quotient scores, IQ scores of 3-year-old children born to mothers who were on this medication during pregnancy. So previous studies suggest that the standard deviation of IQ scores of 3-year-old children is 18 points. Okay, so this is the first given point. So this is the standard deviation of previous study. Okay, is 18 points. Because we are calculating the sample size and we haven't done the study, so we need to rely on previous study, which is basically called literature review. Okay, anyway, how much such children should the researchers sample in order to obtain a 90% confidence interval? Okay, it is 90% confidence interval with a marginal error less than or equal to 4 points. Okay, so what's the margin of error? We got a marginal error here, 4 points. Okay, and then we got standard deviation, 18 points. Okay, so based on the previous slide, we have the formula. Given what is given here, we have marginal error 4 points, and then confidence limit is 90%. Okay, we got Z critical score. Okay, Z score, which correspond to 90%. So it is approximately 1.65. How to find this value? You can calculate using Q norm. Okay, in R, or use the Z score table. And then our standard deviation is 18. Okay, let's calculate something. Okay, so basically we have this marginal error. Okay, marginal error is multiplication of critical value and standard deviation divided by square root of n. Okay, so we want n, so we put it to the left side and we arrange it. Okay, and then we got n is equal to 55.13. Okay, so that is when we want 4 points. Okay, okay, so when we want this marginal error greater, imagine this. Okay, if we want to increase, if you increase this value will go down. Okay, if we decrease it, it will go up. Okay, so when you want to find narrow marginal error, you need larger sample size. Okay, okay, that is the point here. So we need at least, you need to increase, round up. Okay, you cannot round down in this case, you have to round up because we are dealing with patients, human, so we cannot leave it as a decimal point. So we need at least 56 such children in the sample to obtain the maximum marginal error of 4 points. So again, if you decrease this point, okay, if you want to make it narrow marginal error, then you need a greater sample size and you can play around it. Okay. Okay, so we found that we need at least 56 children. What would the required sample size change if we want to further decrease the marginal error 2 points? Okay, we now know that the sample size will increase, but how much? Okay, let's take a look at it. Okay, we have this formula, and then what we want to do is we want to reduce 2 points. Okay, so we want to reduce 4 to 2, so just divide it by 2. Okay, and then imagine this: when you reduce the marginal error by 2, then your sample size will have to increase 2 times. Okay. Next, we are going to look at this example. The General Social Survey asks how many days during the past 30 days was your mental health, which includes stress, depression, a problem with emotions, not good. Based on the response, we have 1,151 US residents, and they reported that 95% confidence interval of 3.40 to 4.24 days in 2010. So how will we interpret this interval in the context? Okay, so they asked this question, and then we got the 95% CI of the US resident. Okay, so we can interpret as usual. Okay, how do we interpret this? We can interpret this, say we are 95% confident that, okay, US resident normally feels the mental health and emotion, or whatever problem it is, within the past 30 days were fall between 3.40 and 4.24 days, okay, out of 30 days. Okay, let's look at it. We are 95% confident that Americans on average have this 3 to 4 days of bad mental health days per month. Okay, this is how we interpret the 95% confidence interval. So next question is, in this context, what does a 95% confidence interval mean? Okay, so what does it mean is that, imagine we are doing 100, we are doing the same study 100 times, okay? And then in 95 times, the true population value, okay, the number of days they suffer mental health. So that true population value were contained between these two range, okay, within these two values. So basically, we can say the 95% of random samples of this American were used confidence interval that capture the true population mean or number of bad mental health days per month. Okay, so again, now we want to increase it to 99% confidence interval. Okay, so if we want to increase the 99% confidence interval, will this new interval be narrower or wider than the 95% confidence interval? What do you think? We want to increase 95 to 99%. Will it be narrower or wider than 95% CI?
Narrow.
So imagine this, as the confidence limit increases, so that the limit of the confidence interval wider. Okay, so 99% confidence interval will be wider than the 95% confidence interval width. Okay, so how to make it? How to make this? That means if we use the same sample size, okay. But if we want to make it narrower, then we need to increase this sample size. So even when we use the 99% confidence interval, it will still give us the narrow value if we have large sample size, larger than this.
Mu.
Yes.
But if we increase the confidence, like if we increase the margin of error, that means if we reach to 99%, then the margin of error decreases. That means the sample size would increase, isn't it? And I didn't get the last sentence, this one.
This one?
Okay. Yes, yes. The reasoning that you provide. Can you please repeat?
Okay, okay. Can you imagine the normal distribution we got? So we got 68, 95, and 99%, 99.7% rule. So right now, with this sample size, we are using 95% confidence interval, and we got this range. But when we increase this 95% to 99% using this sample size, this range will increase. Okay, this range will, I mean, this will go down and this will go up. The interval will be a little bit wider than the 95% CI.
Okay, okay. That means we are using the same sample size.
We are using the same sample size. Okay. If we are using the same sample size and you use 99% confidence interval, the interval will be a little bit, the value will be a little bit, greater or smaller than the, I mean, the lower, it is the lower bound, okay? So the lower bound will be lower, the upper bound will be greater, larger, so that the interval width will be wide, okay? That is basically this one set, okay? Confidence limit increase, so there's the width of the confidence interval so wider. But if you want to remain the same or even narrower, and you can increase the sample size here. And let's look at this example, okay? So imagine if we ask 50 college students, okay, how many exclusive relationships they have been in so far. Okay, we asked 50 college students, so the sample size here is 50. Then And then the student in the sample had an average of 3.2 exclusive relationship, okay? That means they have average of 3 to 4 times that they have been in a relationship with a standard deviation of 1.74. Okay, so if you imagine it, it's a little bit difficult to understand this 3.2 and 1.7 for in a context of having a relationship, right? You either have three or four relationship, or 1 or 2 standard deviation or such relationship. But anyhow, let's take a look at this. In addition, the sample distribution was only slightly skewed, okay, to the right. Okay, this is not population, this is sample distribution, which is a little right skewed. So estimate the true average number of exclusive relationship based on this sample uses 95% CI. Okay, so we have this 3.2. Okay, 3.2, which is a mean, and we got standard deviation. And then we got a sample distribution statement that is a little bit right skew. Okay, and we say that we have to construct 95% CI. Okay, let's imagine, let's think about our condition to use confidence interval. Okay, so first condition is independent. So it only said a sample of 50 college students. Okay, they didn't say about any random number or anything. But anyhow, we can imagine that 50 college student is definitely less than 10% of all college student population. Okay, so we can assume that this is satisfying the independent condition. Okay, so this is the first condition. Second condition, we need a sample size or skewness, okay, we got 50, rho tan is 30, okay, and then the statement is the sample distribution is a little bit right skew. Okay, it's only a little bit right skew, so we have 50 college students, so I think it is also okay for the sample size condition. Now, so we can use the confidence interval formula. Okay. Okay, so this one is basically what I've been saying. Okay, so let's calculate this. Okay, so we need to know standard error. Okay, because this is only, we are only given standard deviation, so we need to calculate standard error. So standard error is coming from sampling distribution simulation. Okay, we divide standard deviation by square root of n, so we got standard error. Okay, so we got this one, and then we got point estimate. Average mean is 3.2. So we point estimate plus or minus marginal error. So we want to find out 95% CI. So the critical value is 1.96, and then we plug in the standard error value, and then we got this 2.72 and 2.68. Okay, so this is how you find the standard error. So basically, confidence interval is not hard. First, you need to know the sample size. You need to know mean, standard deviation. Okay, so if you know these three parameter or statements, then you can find out the confidence interval. Okay, so the final interpretation. What is the final interpretation? We are 95% confident that the college students on average have been in 2.72 to 2.68 exclusive relationships. Okay, that is how you interpret it based on our result. But this has been a little bit annoying, right? Because when you count the relationship is a count, not the continuous variable. So I think it's really important to understand this, even though they stay like this. But it's rather nice to stay like this, okay? 3 to 4. Okay, So we can say that on average, college students on average have been in 3 to 4 exclusive relationships, something like that. Okay. It's like we cannot exactly half the relationship, exclusive relationship. So it does seem like they are a little bit cheating, right? They have 2.7 relationship. It's a little bit tricky to interpret. Anyhow, I think this is the end of today. Tomorrow we will continue with the hypothesis testing. Okay, which is basically p-value, right? So we got this 95% CI. Okay, we got this 95% CI, and then we want to see how significant we want to test. Okay, we want to see something if the mean, if this mean 3.2 mean is different to the population mean or to another mean from another sample. Okay, we are going to test whether the two value are different or not. Okay, and we will interpret this by using p-value. Okay, so tomorrow we will talk about hypothesis testing. That will be day 5, and on day 6 and day 7, I think we will go into t-test, student t-test. So there are separate, I think there are several types, like student t-test for independent mean and pair t-test or t-test for dependent means. Okay. Okay. Anyway, which condition do we use t-test, and what are the conditions, and if our data does not meet the condition required for this t-test, then what do we do? Okay, what are the non-parametric tests for each t-test? And again, we can look at if we have 3 means. Okay, if we compare means more than 2 groups, then we use ANOVA. And then what is the condition to use ANOVA and how to interpret ANOVA? I don't really go into detail about the mathematical formula and how to calculate manually all these t-tests, ANOVA, and all this stuff, but we will talk about what it is and where we can use it, and then how we can interpret the result, and how can we check whether our data met the assumption or not, or the conditions or not. Okay, I think that's it. Tomorrow we will talk about p-value, and then on day 6 we'll talk about t-test, and on day 7 we'll talk about ANOVA. And then next week we will discuss linear regression. I think on linear regression I will talk about a little bit about how we can, what are important to understand the linear statement, and using it graphically and using some mathematical formulas. But anyhow, we won't go into details, but we have 1 whole week for linear regression, so let's see. Okay, so any questions on today's session, or any other questions? Okay, you're welcome. Okay, anyhow, so this is it. So let's call it a day, and then